Hello friends, let's continue with sampling. In this lecture, we will talk about aliasing, which is the effect of undersampling. We know that a sampler converts a continuous time signal into a discrete time signal. We have seen the process of ideal sampling or impulse train sampling, in which a continuous time signal is multiplied with a periodic impulse train, and the result is the sampled version of the continuous time signal. In frequency domain, this process of sampling results in generation of infinite copies of the original spectrum. If the successive copies of the spectrum do not overlap, then it is possible to recover the original spectrum by using a low-pass filter or by using an ideal low-pass filter if the successive copies just coincide. That is when fs minus w is equal to w, that is fs equal to 2w. So in general, for perfect reconstruction of the original signal from its samples, the sampling rate should be greater than 2 times the maximum frequency of the original signal, and this very important result is known as sampling theorem. In general, when the sampling rate is greater than 2 times w, then we call it oversampling. When it is exactly equal to 2w, it is perfect sampling. That is, here we can use an ideal low-pass filter to extract the original spectrum. So this frequency is fs minus w, and this is w. So if fs minus w is greater than w, then we say it is oversampling, and we can use a low-pass filter, a practical low-pass filter with some transition band, such that the cutoff frequency of the low-pass filter is greater than w but less than fs minus w. Then we can recover this spectrum, and therefore we can get the original signal back. Even it is possible in this case when fs is exactly equal to 2w. Of course, there are some cases in which for this case it will not work. We'll talk about those cases separately. But in general, as long as fs is greater than equal to 2w, in principle, it is possible to reconstruct the signal perfectly from its samples. Of course, fs equal to 2w, even if it is possible to reconstruct the signal in this case, that will require use of an ideal low-pass filter, which is unrealizable because it's a non-causal system. Moreover, it is also unstable. So an ideal low-pass filter can never be realized, and therefore, for this case, when fs is exactly equal to 2w, practically we will not be able to reconstruct the signal. But when fs is greater than 2w, that is the case of oversampling, it is possible to reconstruct the signal. However, when the sampling frequency fs is less than 2w, less than the Nyquist rate, in that case, the successive copies of the spectrum will overlap as shown here, and because of that, even if we could use an ideal low-pass filter, it will not exactly recover the original signal, and there would be some distortion. This distortion is known as aliasing. So remember, this overlap causes aliasing. Overlap is not aliasing. What exactly we mean by aliasing? The term alias means an assumed name. It is a false identity, and aliasing is the phenomenon of a high frequency component in the spectrum seemingly taking on the identity of a lower frequency. Let us understand it through an example. Suppose this is the original continuous time signal, which is a sinusoidal signal, and suppose we take its samples at a sufficiently fast rate, oversampling case. So these dots are showing the samples of the signal. This is a time axis. So these are the samples taken at a rate sufficiently higher than the Nyquist rate. So if given these samples, we can perfectly reconstruct the original sinusoidal signal from here. However, for the same sinusoidal signal, if the sampling rate is made smaller than the Nyquist rate, as you can see here in this second case, suppose we are taking for this original signal, if we take sample at these points shown by dots here, this and then this and then this, you can see that we are taking the samples at a rate lower than the Nyquist rate. For Nyquist rate, we should take at least 2 samples per cycle, but here we are taking 2 samples in 4 cycles, and therefore the sampling rate is sufficiently smaller. This is the case of undersampling. Now, if these samples are given, and if we are required to reconstruct a signal, continuous time signal from it, it would be this signal and not the original one. So this is the reconstructed signal. Clearly, the reconstructed signal is not the same as the original signal. Moreover, it has a lower frequency compared to the original signal. This phenomenon is called aliasing, and that is what is written in the definition here. So let us reread the definition. It says that aliasing refers to the phenomenon of a high frequency component in the spectrum of the signal seemingly taking on the identity of a lower frequency in the spectrum of its sampled version. And therefore, remember that this aliasing is caused because of this overlap, but aliasing is not this overlapping. This overlapping is causing aliasing. So this overlap of 2 successive copies of the spectrum of the sampled signal causes aliasing, which is the phenomenon of a higher frequency component taking on the identity of a lower frequency signal, and which is essentially a distortion. Let us understand this phenomenon through another practical example. Think of a wheel with 10 spokes as shown here, and the spokes are numbered 1 to 10 in the clockwise direction. Suppose the wheel is rotating in the clockwise direction. And how do we perceive it to be rotating in the clockwise direction? Our eyes take samples of this movement. Suppose we fix our eyes here where 1 is written, and it is moving at a speed such that after 1 we observe 10, and then we observe 9, and then we observe 8, and so on. And because of that sampling done by our eyes, this wheel appears to be rotating correctly in the clockwise direction. Now suppose we increase the speed of this wheel, we double the speed, so that after 1, the second sample that we observe is 9 and not 10. We don't see 10. After 1, we observe 9, and then 7, and then 5. So now the wheel still appears to be rotating clockwise correctly and at a speed double than the previous case. Of course, in this case, the sampling rate relatively has become 1/2 of the previous case. If we continue to increase the speed, see, we want to study the effect of sampling rate on the movement that we perceive. If we further increase the speed, that is relatively, we now have decreased the sampling rate. After 1, we observe 7, and so on. The wheel still appears to be rotating in the clockwise direction. Now, what happens if we further increase the speed of the wheel such that after 1, we observe 6? After 6 again we will observe 1, and then 6 and 1. Now what happens that time? Now It is the situation where our vision deceives us. Because after 1, we can observe 6 if the wheel is rotating clockwise or if it is rotating anti-clockwise. The same way. And therefore, we get confused. Sometimes the wheel appears to be rotating clockwise or sometimes anti-clockwise. Now, if we increase the speed further, such that after 1, the next sample that we observe is 5, the wheel is still rotating clockwise. So after 1, we observe 5. So actually the wheel has rotated clockwise, but our eyes act as a low pass filter and our eyes perceives this rotation to be a counterclockwise rotation, as if after 1 we are observing 5 in this way. So the wheel now appears to be rotating in the anti-clockwise direction. And that's not all. If we further increase the speed such that after 1 we observe 4, the wheel is rotating clockwise, but because of the low pass filtering done by our eyes, we observe that we perceive this movement to be in the anti-clockwise direction. And earlier, after 1 we were observing 5 and now we are observing 4. Actually, the speed of the wheel has increased in the clockwise direction. We perceive the rotation to be in the anti-clockwise or counterclockwise direction, and the speed appears to be decreasing. This is what is called aliasing. It does two wrong things here: wrong speed and wrong direction. So I hope this idea of aliasing is clear. How can we avoid this effect of aliasing? There are two ways. First, go for oversampling, that is, sample at a rate sufficiently larger than the Nyquist state. And second, use anti-aliasing filter. Anti-aliasing filters are actually low pass filters which will remove some undesired high frequency component from the signal before we do sampling. And once that is done, then we need to go for, of course, this case, and the highest frequency component that is present in the signal after this low pass filtering has been done to remove some undesired higher frequencies from the signal. We will go for the sampling at a rate which is greater than twice the maximum frequency now present after the low pass filtering has been done. So these are the ways to avoid aliasing, and therefore anti-aliasing filters always are present in any digital communication as well as digital signal processing systems. So that's all for this lecture. Thank you.